So okay, so we have seen that degree of stability for a, for an isolated system. I have showed you that how that your degree of stability, that is the eigenvalues, real part. I mean, in general eigenvalues which is very close to the origin and lying on the left half of the S plane, and by varying the integral controller k eigen setting, that we can shift that eigenvalue as much as possible away from the origin, right, and that is actually we define degree of stability, and based on that we are getting some optimum values of integral controller gain settings. Now, in that case, this is the only thing I have told, but there are many other like many other techniques to obtain the optimum values of integral controller gain settings, that will give much better response than what has been shown, but those things are not possible in that classroom, because you need to write coding and then you have to see how things are happening. Similarly, for if you use PI controller or PID controller or a combination of your integral and derivative action, for that also it is not possible to do that exercise in the classroom. You need computer and you need some optimization technique. So those things cannot be taught here, right. But general thing is, as far as things are concerned, the classroom exercise, and hope you have understood this. Now, next is the composite frequency response characteristic, right. For example, before showing this, suppose you have a system, just isolated system, not interconnected with anything, and you have the load, say this is the load, right, and you have many generators, suppose they are connected, suppose you have many generators, they are connected and they are supplying this load. So this is your load and this is your generator, generator 1, generator 2, generator 3 and so on, and you have to find out what is the composite frequency response characteristic, right. In this case, so many generators are there and they are in parallel. So we will assume that all the generators are in coherent group, that means they swing in unison, that means their increase or decrease of the speed remain same. So that means now we will come to the composite frequency response characteristic. So suppose you have n number of generators, right, and supplying a load. Just now I showed you that suppose you have these 3 generators and this is the load. You may have in general, if you generalize it, suppose you have n number of generators. So in that case, how the block diagram will be, because single area block diagram we have seen, and we will consider here, to just to save the space, same thing, right. We have taken this non-reheat type turbine, that this is the governor time constant, and this is the non-reheat type turbine, the steam chase time constant, right. So suppose you have in this case, earlier for single area case or your isolated case, only one PG, that is delta PG was there, but you have n number of such units. So things are very simple. For example, this part Kp upon 1 plus STP, it will remain same, because you have, suppose you have 3 generators, they may have your different H, the inertia constant H1, H2, H3, and of course you can find out the equivalent H of this thing. One numericals previously you have shown, and in the power system analysis course, in the your previously which I recorded, that thing you have seen it, that for transient stability analysis, that how to obtain the H equivalent has been shown there. So if you have a H1, H2, H3, it can be represented by an H equivalent and only a single your what you call that power system time constant and one single Kp, right, that is this one. So even if n number of generators are there, this block will be only single block. So Kp upon 1 plus STP, assuming that H can be equivalent H you can obtain for all the parallel connections, right. So this is single one, and it can be, I told you, all the generators are swinging in unison, so they can be represented by a single frequency, right. So there is a single frequency deviation we have taken, and even if you have different H1, H2, H3, their equivalent can be obtained, right, they are in parallel. So and in that case, your this power system transfer function we call, right, Kp upon 1 plus STP, it will be single one. Now, and different unit, they may have different governor or turbine time constant. So it has been taken like this. So earlier we have seen for isolated case only one U was there, but you have so many units are there, So input to each unit is U11, U22 up to UNN. What is U11, U22, UNN we will see later. Now all this the plus feedback, and now from here this is for unit 1, it is 1 upon r1, this delta f is coming 1 upon r1. Similarly, for unit 2, this delta f is coming here 1 upon r2, and similarly for nth unit, I made it this way. So it is 1 upon rn, that is your this feedback for nth unit, and here it is unn, and here you have this is for first unit, this is for second unit, this is for third unit, and this is your generation for unit 1 delta Pg1, generation for unit 2 delta Pg2, and generation for unit 3 delta Pg2. Sorry, in nth unit it is delta Pgn. That means delta Pg1 plus delta Pg2 up to delta Pgn, this summation, and this is the load here, only single load. I told you only single load is here, right, and that is your single load, and it can be, a whole thing can be represented by a single time constant, because single h we can make it, and therefore Kp upon 1 plus STP, and the output is the delta f, the frequency deviation. This is actually very simple diagram. Actually, so you should not be very very much worried about looking at this diagram. This is very simple. First you draw for like the way you did for single area system. Instead of your what you call delta Pg, make delta Pg1. This is the first one, and delta f is same from everywhere. From delta f 1 upon r1 come, from delta f 1 upon r2, from delta f up to nth unit 1 upon rn, same feedback, plus minus, and this is u11, u22, unn. What is this? I'll coming now. So this is figure 15. This is multi-unit isolated power system. It is not interconnected with anything. As soon as you interconnect the power system, the tie line model, tie line means that is 3-phase transmission line, right, and if two power systems are connected by tie line, we call, right. So those models will come later. So this is your now what you call that isolated block diagram for multi-unit system. You have so many generating units, so this is multi-unit system, right. Now for uncontrolled system, I mean when system is not uncontrolled, u11, u22 up to unn, all will be 0, So for uncontrolled system, u11, u22 up to un is equal to 0, right. So at steady state, s tends to infinity, that is s tends to 0 as steady state, right. So that means t tends to infinity, right. So delta Pg1 1 SS is equal to minus delta FSS upon R1. This we know. Earlier for single unit we have seen delta PGSS is equal to minus delta FSS upon R, but that is so many units are there, but meaning is same. So I mean when u1 is 0, and if you make all the block diagram that s your t tends to infinity, so s tends to 0. If you make all s 0, so same philosophy will be applied here. So delta Pg1 SS is equal to minus delta FSS upon R1, delta Pg2 SS minus delta FSS upon R2. Similarly for nth unit, delta Pgn SS is equal to minus delta FSS upon Rn. This is known to us. Now steady state value, now here when all the in the block diagram, if you make s is equal to 0, you can do yourself. So this is 1, this is 1, this is 1, this is 1, this is also 1. And steady state value delta Pg1 SS, delta Pg2 SS, delta Pg up to delta Pgn SS, add all minus delta PL into Kp is equal to delta F SS, right. So here it is delta Pg1 SS plus delta Pg2 SS plus up to delta Pgn SS minus delta PL into K bracket close into Kp is equal to delta F SS. For single area system only delta PGSS was there, right, and these things were not there, but you have n number of units. So delta Pg1 SS, delta Pg2 SS up to delta Pgn SS, right, sum it up all minus delta PL into Kp is equal to delta F SS, because at t s tends to your what t tends to infinity, s tends to 0. So in this block diagram you can make s is equal to 0 also, and this is your all use 0. So that will give you a steady state block diagram, not showing here, but it is understandable to you now, right. So that means, and Kp is equal to 1 upon d, Kp is equal to 1 upon d. If you put here Kp is equal to 1 upon d, then it will be multiplied by d delta FSS. So it will be d into delta FSS. So that's why we are writing d into delta FSS is equal to this one, and this one delta Pg1 SSS, delta Pg2 SSS up to delta Pgn SS. You substitute here. All this is put it here. So this is you put it here, and the minus delta FSS upon R1 minus delta FSS upon R2 minus up to minus delta FSS upon Rn minus delta PL, right, or upon simplification, or delta FSS is equal to minus delta PL divided by d plus 1 upon R1 plus 1 upon R2 up to 1 upon Rn, right. So this is the steady state, or what you call if it is a composite system, I mean so many units are there. So, this is the expression for the steady state error. So, in that case what will happen, that I will come to that. So, this is your same as before. If you have only one unit, then this 1 or 2 1 r n term will not exist. It should have been become d plus 1 upon r minus delta p l, but because of so many units are there, so that is why minus delta p l upon d plus 1 upon r 1 plus 1 upon r 2 up to plus 1 upon r n, or you can write that delta f s s is equal to minus delta p l upon d plus 1 upon r e q. This form you can write. Earlier for single unit we are writing minus delta p l divided by d plus 1 upon r, but instead of r you make 1 upon r e q, and where r e q is equal to, you can make 1 upon bracket 1 upon r 1 plus 1 upon r 2 plus up to 1 upon r n. Just simplifying this equation, just simplifying this, putting in the for d plus your 1 upon r e q, and your r e q we are putting actually 1 upon r 1 plus 1 upon r 2 up to 1 upon r n. So, 1 upon r e q actually will be 1 upon r 1 plus 1 upon r 2 plus 1 upon r n. I mean this thing, right. So, for isolated system, the function of ellipse is to restore system frequency to the specified nominal value, and this is accomplished by adding a reset or integral controller, right. So, before that just have a look, that your delta f s s, actually delta f s s I am writing here, delta f s s is equal to your minus delta p l divided by d plus 1 upon r 1 plus 1 upon r 2 plus up to 1 upon r n, say, right. D is actually very small, right. So, because it is Kp, Tp all we have seen, Kp we got that is your 120. So, D will be 1 upon 120. So, D is very small. So, this can be just look at that, this can be approximated, say, I mean approximate 1 minus delta p l if D is neglected, assuming that D is approximately 0. So, in that case it is 1 upon r 1 plus 1 upon r 2 plus up to 1 upon r n, right. For example, if you assume r 1 is equal to r 2 is equal to r n is equal to r, right. If you assume all, then delta f s s will be minus delta p l divided by 1 upon r plus 1 upon r, right, up to your 1 in a nth term, right, up to it will go to that your what you call nth term. That means say it is up to nth term, right. That means this one actually will become minus delta p l divided by n divided by r, right, because you have n number of 1. That means it will be minus r into delta p l divided by n, right. That means if n is equal to 1, that is the single unit, whatever you have seen earlier, in that case steady state error will be minus r into delta p l, but when if it is more than 1, then basically steady state error of frequency is your decreasing. That means your delta f s s is equal to, say, suppose your delta p d delta p l is equal to, say, 0.01 and r is equal to 2.4, say load increase. That means this one will be minus 2.4 and say n is equal to 1, right. So, minus 2.4 into 0.01 divided by 1. So, delta f s s is equal to minus 0.024 hertz, right. So, if n is equal to 2, suppose if n is equal to 2, so it will be delta f s s will be minus 0.012 hertz. So, that means if you put more units in parallel, the steady state error is actually that value is decreasing, right, it is decreasing. So, that means your that departure of the system frequency from its nominal value will be less if you just what you call, if you just make it your if you put more units in parallel. So, that means what, this value will decrease if you have more than 1 unit, this value will decrease, right. So, that is advantageous if more in general you will find more units are operating in parallel, not 1, maybe not 2, maybe more than that in any power system. Now, this is but the steady state error will exist. If you even if you put 3-4 units, steady state error will be there, but your objective is to eliminate the steady state error. To eliminate the steady state error, what you do? You need integral function, integral action. So, what we can do is that your integral controller suppose is needed. Actually, actually for a thermal power plant, right, generally integral control only integral control action is recommended, and also proportional is also possible, but derivative control action for thermal power plant actually generally is not recommended, right. So, reasons, what is the reasons, another thing beyond the scope, then we have to go much into detail, but for thermal power plant generally utilities they prefer integral controller having very small gain setting. Reasons I will tell you later. So, but you have to go for integral control action, right. So, in that case what will happen, suppose that U11, U22 up to UNN, suppose you have this block diagram, no, earlier we have this block diagram, this is your U11, this is U22 and up to UNN, n number of units. So, from where this U11 U2 is coming, actually this is your frequency deviation delta f, and this is your integral controller minus Ki upon S, and this is U, right. And so, U11 and your this U actually your what you call in part of that is going to unit 1, going to unit 2 and going to unit n. So, this is U and this is U11 actually A1 into U, U22 is equal to A2 into U up to UNN is equal to N into U. So, this is structure of the integral controller. Basically, we have seen that in general the steady state value of U actually is equivalent to your load demand, right. That we have seen also. I have for isolated system I have shown you that steady state value actually is equal to load demand. So, suppose load demand is say for example for your 10 megawatt, right. So, a steady state you also will show 10 megawatt, right, and and this 10 megawatt this has to be shared by this unit, among this unit the 10 megawatt has to be shared. So, in that case you and this A1, A2, AN whatever it is, you if you set arbitrary value, suppose it A1 plus A2 up to AN, its summation should be 1, and if suppose load suddenly 10 megawatt load is increased, for example, then 10 megawatt you have to share among this unit such that your fuel cost will be minimum. Again I am telling you that again that economic load dispatch concept is coming here, but what we will do, that means, and just instead of setting arbitrary values of A1, A2, AN, if you get how much, suppose out of 10 megawatt how much, that suppose you have instead of n units, suppose you have 3 units and every unit has its different fuel characteristic. So, accordingly after economic, suppose 10 megawatt, how you can distribute among these 3 generating units such that fuel cost will be minimum. So, in that case this A1, A2, AN you have to decide, but just I am telling you for the sake of understanding, suppose you have a 10 megawatt, right, 10 megawatt power demand increase, and suppose this A1 if you put 0.4, this is you 0.4 and this is your 0.2, because summation should be 1. So, this one what will happen, U11 output will be 4 megawatt, then 4 megawatt and 2 megawatt, that means this unit actually will generate 4 megawatt, this unit will generate 4 megawatt if it is a 3 unit system, and this unit will generate 2 megawatt, right, total will be 10, because disturbed load increase is 10, right. So, that means this A1, A2, AN you have to set, but its value will be less than 1, and if anything you set it to 0, for example, suppose 3 units are there instead of nth unit, suppose this is your third unit, and if you put this one is 0 and this was say 0.4, this is 0.6, so it will be your what you call that for your 4 megawatt it will be 6 megawatt at steady state when you will go for transient response. That means this generator will generate 4 megawatt, this will generate 6 megawatt, this will not generate anything at steady state, but at during transient it has some effect, because it's transient it will swing, right, some oscillation will be there, after that it will be settling to the steady state. So, if this generator is not your what you call responding to the steady state to the increase of the load, but transient with transient some your what you call this generator will show that is generating some power, but at the steady state you will find this is 0. So, that is why this is the control structure, and this is your an input to this controller is delta f, the frequency deviation, because our objective is to correct the steady state error in frequency to 0. So, hence this U11, U22 and UNN all will all you have to going to the input to the each unit, this one, the U11, U22, suppose if you have n number of units then UNN, right. So, this is actually your what you call the structure of the controller. That means that's why I have given let A11, A12 up to n are the participation factor we call, right, and A1 plus A2 up to An summation of all A is equal to unity, just I told you. And at steady state I told you that U is equal to U steady state is equal to delta PL. This we have seen also in the for the single area system, this has been shown. Therefore, the steady state output of each generating unit can be given as delta, I just told you delta Pg1SS will be A1 into delta PL, delta Pg2SS is equal to A2 into delta PL, and delta Pgnss is equal to An into delta PL, right. So, these are the steady state power generation by the generators. If you go for simulation, you will see that your what you call this power has been generated by this generator, right. So, that is that your what you call this is that your composite system. Another thing is there, if time permits, I will tell you those things, that generally particularly for thermal power plant, hydro power plant we cannot consider in this course, then it will take long time. So, only we will restrict ourselves to the thermal power plant, right. So, these are all steam turbine generator, but if you consider hydro power plant, then in that case the hydro governor is a different type, right, and hydro turbine also have different transfer function. So, we will will not consider that, we will only restrict to ourselves to the your what you call steam turbine, right. So, every generator cannot generate power the way you want, right, because you have a lot of your what you call that your physical constant, right. I mean we just if you ask that power can be generated in 10 megawatt just in 1 minute, it is not possible for the generating units due to its many physical constants are there. That is why that power that output of the generator whatever we have shown here, that we have not considered that your what you call that those rate limit, because it has some generation rate limit. Later I will show you how it can be incorporated, but it is at that time as soon as you consider that your rate limit, the system will become non-linear. So, we do not want to do that here, but as soon as any non-linear, because this is a non-linearity, because every generator has some restriction. When you go for simulation, those restrictions you have to impose at that output of this your what you call this power generation. Another thing is there, this is the governor model we have seen. Those things I will not cover, but giving some ideas that every governor has dead band, right. Dead band means the magnitude of sustained speed change within which there is no change in the valve position, right. So, the dead band is there. So, if you put if you consider the governor dead band, right, it has some mathematical analysis, but here we will not consider. If you put generation rate limit, if you put governor dead band, then in the response you will see a very long sustained oscillation, right. Instead of going, it will go steady state, it for after long duration, right, because of the dead band, because dead band actually gives that long sustained oscillation. Although it is stable, its amplitude is small, but it will provide your what you call sustained oscillation. So, those things are there in AGC, but we will not consider. Even this controller also for any system, any system you take in reality, basically all systems are continuous system. Even power system itself is a continuous system, right. But this controller part is always in discrete domain, because if this output whatever you give it to the feedback to the controller, whatever feedback this is you are giving, actually this is actually sampled at every sampling instant. And for AGC you will find it maybe sampling instant maybe 1 second, 2 second, 4 second, 6 or 8 second whatsoever. Even it can go up to 32 seconds, that your sampling instant, and accordingly that controller will operate, right. Even this U also it can instead of giving continuous feedback to the unit, it can give it after some sampling instant, right. So, those things are beyond the scope, but giving you some ideas regarding this concept. We will only consider about your what you call the linear power system. Next whatever we will consider, we will consider that your what you call interconnected operation of power system. That means two power system or n number of power systems, suppose they are interconnected, for example, and then the concept of control area actually coming. For example, suppose you have a power system, and you have another power system, right. You have another power system. Suppose this is your area 1 and this is your area 2, and here you have voltage V1 angle delta 1, V1 angle delta 2, and this line we call actually tie line. This is a single line diagram. So, basically here this side a power network, very huge network, they are all power network interconnection is there, this side it is interconnection is there, right, and in between that these two power system are interconnected by tie lines. Tie line means basically it is a 3-phase transmission line, right, and load is here and load is here, they are interconnected. Suppose this is my area 1, I am putting delta PL1 and this is the load at area 2 delta PL2. Then suppose this it is expected that this power system or this area will accommodate its load by its own generation. Similarly here also, right, but question is that if this suppose this demand is more and this area whatever is power generation capacity is there fail to meet the load demand, then additional demand will come from this area, assuming that this power system has sufficient spinning reserve such that it can supply its load, right. So, if it is so then in that case the power will flow through the tie line, that means it is helping this area, or in other way also, that is that your interconnected operation actually the main benefit is the cooperative assistance between these two areas. In general you have so many areas, right, so they are interconnected. So, this is the advantage of your what you call that when two power systems are your what you call that interconnected. It may have so many areas, suppose this one, this is another area, so it may be connected like this, it may be connected like this. So, if you make more connection by all these tie lines, suppose this is power system 1, this is power system 2, this is power system 3, this is power system 4. So, all these things can be connected together, right, such that one can help each other. So, that is the cooperative assistance actually is one of the planned benefit of interconnected power system. So, that is why we will move to your what you call that your interconnected operation of your power system. So, we will consider in this course we will consider only two area system, well, that means two power system interconnected like this. This one we will not consider because it is not for the classroom purpose, the modeling will be block diagram representation will be much bigger and analysis will be little bit lengthy. So, we will only restrict to the interconnected operation of this one, right. So, in that case what will happen that I told you that 2 area 3 area whatsoever the concept of control area comes. So, consider a practical system with number of generating station and loads, right. I mean this system, this area 1, this is actually area 1, this is area 2. So, in this system there are many generators because it is a power system, it is a huge power system, right. Suppose you have one, so for example, suppose one power system you have in Chennai, another is in Bangalore, and suppose two power systems are interconnected by this 3-phase transmission line, right. So, this is and in power station you have so many generators, right, and interconnection, all the substation loads, everything is there here also there, but they are interconnected. I mean if I need power I can purchase from this area or from this area, either of this area. So, it is a planned benefit, right, for the interconnected operation, the cooperative assistance. It helps actually rather than you have accommodating this, but it is expected that all the generation in that particular area will accommodate its own load disturbance or own load increase, right. So, in this case the concept, that is why concept of control area coming, whatever I am telling, right. So, LFC problem of a large interconnected power system has been studied by dividing the whole system into a number of control areas, right. For example, this one I just showed you, maybe it's this thing you just divide it different region and this is can be divided, right, in a number of control areas. So, that means a control area actually defined as it, so it may be a power system, it may be a part of the system or a combination of system to which a common generation control scheme is applied, right. That means each area whatever you have that you can apply a common generation control scheme, right. So, it may be a power system or maybe a part of a system or maybe a combination of system to which a common generation control scheme is applied, right. So, this is the concept of control area. Area means it is basically a power system or part of a power system, right, where generating stations are there and it is and so many several loads are also there. It is like a power system network actually concept is, but this is the concept of control area, but all this a common generation control scheme can be applied, right. So, the electrical interconnection within each control area are very strong, right. That means it is a power system network. It is a power system network. You have so many transmission line connected, right. You are among various bus bars, right, among various bus bars. It is a power system network. right. So, and your what you call with each contour layer very strong as compared to the tie lines with the neighboring areas. Tie line means only this one, only it is connected like this. So, only few lines, where in each one is a power system, you have several bus bars and several transmission lines are connected, right. So, and all the generators in a control area, they swing in unison, right, or coherently, and it is characterized by a single frequency. That means they are in coherent group, they swing in unison. That means their increase or decrease in speed is remain same. That means they can be characterized by a single frequency. This is the assumption. And in normal steady state operation, each control area of a power system should strive to meet its load demand. I told you, under normal operating condition, that suppose load demand is here, this PL2, PL1, whatever generating units are here, it should accommodate its own load. Same is here under normal operating condition. But if I need power or some load demand sudden increase, then I can borrow power from the adjusting your what you call from the neighboring areas if I have sufficient spinning reserve. Thank you.